AP Calculus AB, Unit 69, lesson, warm up first. So why don't you guys try this warm up problem, these three problems, and pause the video, and then I will go over them. Okay, so I will assume that you've tried it now. If f is continuous, it means graph is connected and everything. And they give you the derivative. They gave you the derivative. That's really nice. Then fx has a relative max at where? So this derivative's already done. It's factored for you. I mean, wow. This is, they've done a lot of the tedious work for you. So the roots are 0, -2, 3, but watch out for that bounce. I'm going to do a line check, label the line check in order left to right, smallest biggest, -2, 0, 3. Don't forget the 3. Test, x equals 4. It's all positive, stays positive, negative, positive. Draw some little arrows. These are slopes, right? So increasing, decreasing, increasing, increasing. Relative max. See the peak. Relative min. See the valley. That's just a plateau. So f of x has a relative max at x equals -2. And we're essentially using the first derivative test for relative extrema. We're not really explaining it though. So there you go. Take advantage of that. F is increasing where? Well, we're going to do pretty much the same kind of work. We got to take the derivative, 1 over what's inside, times the derivative of what's inside, chain rule. So we get 2x over x squared plus 1 equals 0 undefined. So x equals 0 is a critical point. This is going to give you x equals plus or minus I, so we're not going to use those. This is your critical point. We're going to do a line check. Okay, 0, test a point. X equals 1, positive, negative, so it's going like that, it's going like that. It's decreasing, increasing, relative min. So we want to know where it's increasing. So it's increasing on 0 to positive infinity as long as there's no domain issues. Are there any domain issues with this? I mean, natural log, the inside's notorious, has to be positive. If you were to solve this, you would get plus or minus I. You could do a line check and just test any value like x equals 0, and it would be true the whole time. The domain is all real values, negative infinity, positive infinity. In other words, x squared plus 1 is always positive no matter what you plug in for x, positive, negative, 0, whatever. Okay, interval notation. Okay, next one we're going to sketch. They give one like this every year on the AP where they give you the derivative and they ask you all kinds of questions. Like for sure, one of your first response questions is usually based off this, and probably many multiple choice. This is the graph of f prime. This is the derivative graph, okay? I would just start labeling it. F prime is positive, it's increasing. F prime is negative, it's decreasing. F prime is negative, it's decreasing. So we're looking at these values, the y values of this graph, as the f prime value. So if it's above the x-axis, it's positive. If it's below, it's negative. This is a critical point. This is a critical point. This is a critical point. It's increasing, going up, and then going down. So this has to be a relative max. Okay, it's decreasing, it flattens out, and it's decreasing more. That's a plateau. The concavity is the slope of, is the derivative of the first derivative. The second derivative is the derivative of the first derivative. So if we have a graph that slopes already, the slope of this graph is the second derivative. So whenever this graph is going up, second derivative is positive, concave up. Whenever this graph is going down, second derivative is negative, concave down. Whenever this graph is going up, f double prime is positive, concave up, down, second derivative is negative, concave down. And then you got to identify the inflection point. So I just cranked all this stuff out, and that's what I would usually do, is just write all the stuff down, then answer the questions. It should be easy. Relative max at x equals 2. Inflection point at x equals, wherever the inflection, the concavity changes, 1. 3, and 4. Where is it increasing? Well, it's increasing from 0 to 2, include the endpoints. And that's it, 0 to 2. Concave down, it's concave down from 1 to 3, and also 4 to 5. So if you can label it all in the graph, you can crank the answers out. So I will for sure give you a problem like this in your next test. Now, trying to sketch the original graph from the derivative graph, we talked about this a little bit yesterday. You're going to have to actually do it more coming up on homework. So I would write all the stuff on the graph, at least concavity increasing, decreasing. So we got to figure out where to start. We got to start some arbitrary C value, okay? So is it going to go up or down? Is it concave up or down? So this first chunk, it's going up and it's concave up. So I break it into little chunks, maybe even like almost like little quarter circles. I mean, we can make this graph better, but this is as good as I need right now. It's going up and it's concave up. Then it's going up still, but it's concave down. Some people think, oh, it's going down. Nope. F prime is still positive. Now it's going down and it's concave down. Okay, it should be a smooth connected graph here. Okay, next one, it's going down, but it's concave up. And then it's going down and it is concave down. So something like that. This is the original graph that would give that derivative graph. Let's try another one. And let's see how you try it first. Okay, let's just see what you can do. I'd label this graph and draw the pictures. So pause the video and try it yourself. So I'm going to say, all right, well, F prime is negative, decreasing. F prime is positive, increasing. F prime is negative, decreasing. Critical point, critical point, critical point. Concavity, F double prime is positive, concave up. When the graph of this, when the slope is negative, that's the second derivative negative. Concave down. And this one, F double prime, concave up. So I think I should be able to answer. I mean, I can put more stuff on here, relative maxes, mins, inflection points, but as far as graphing, I think this should be enough. So the first chunk, we got to start at some arbitrary C value. And it doesn't really matter where you put it. I wouldn't put it at 0. I mean, just make it something positive. So first chunk is going down, the concave up, right? Next one is going up and concave up. Next one is going up, concave down. Next one's going down and concave down. Next one's going down and concave up. Something like that. Now, by the way, this looks almost like some kind of trig curve. I mean, that kind of looks like a upside down cosine curve. Wow. That kind of looks like negative cosine, right? And derivative of that would be positive sine, which looks like, well, okay, you got to think of the other way. What would you take the derivative of to get cosine? It'd be, to get negative cosine, it'd be negative sine. So this looks like an upside down sine curve, right? With a shift. But when you take the derivative of the shift, whatever it is, 5 or 10, that goes away. You don't see that in the derivative. Now, technically, this is one of infinitely many possible graphs. Could be any version shifted up or down of this. Okay, it's that plus C issue when you integrate. Now, if you wanted to, and later in this year we're going to actually do this, we could kind of graph a graph that shows all the possible, a bunch of the possibles. So this is like one of a family of curves that all look like this, but it could be any of these. It could be that, it could be that, right? And we actually have a name for this called a slope field. And we'll talk about these later in the second semester, where we actually make graphs that kind of show like all the possibilities. Okay. So on the back, we're going to bring up something that we've talked about before in previous units, but now we're going to sort of, I guess now's the our first official lesson on absolute extrema, absolute maxes, min. So relative extrema are just the peaks and valleys, which we usually use the first derivative test. But let's use an example. Let's say this is like a picture of a mountain range, okay? Now, mountain range, sometimes they're really sharp peaks, sometimes they're nice and rounded. I'm going to take a picture of this, and let's see. I'm going to, let's see. I'm going to take a picture. So this is like the edges of the picture. Okay. Now, the absolute maxes mins could happen at these critical points where the slope is 0, horizontal tangent, right? Or even here, the slopes don't agree. It's sharp. That's a critical point, right? F prime equals 0. F prime equals 0. F prime is undefined. F prime equals 0. F prime equals 0. And these are all peaks and valleys. So this is a relative max. This is a relative min. This is a relative max. This is a relative min. This is a relative max. So the highest point might be one of those, lowest point might be one of those, but it might also be the edges, the endpoints. We have to keep those in mind. They might be the highest and lowest point. The endpoints of the picture. You got to have edges that would have endpoints. So it might be one of those. So what we say is we say that these are the candidates for the extreme value. The candidates might be CPs, critical points, right? Might be a peak or valley. And we find those when f prime equals 0 or undefined. Or it might be the endpoints. And in this case, the absolute max is this. This is the absolute max right here. This is the highest point of the whole graph. But for the minimum, it looks like it might be this one. This might be the absolute minimum. Might be the edge over here. Right? So it might be a peak or valley, or it might be. Now, depending if you change the picture, it's going to change. So like if we change the picture to this, well, that's still the absolute max, but the absolute min is now this guy, right? So if we change the picture, the boundaries, it changes where the absolute max and min are. Of course, we still have some other critical points that we might not even be looking at that are outside of the picture, right? So anyways, that's what we're doing, okay? So the candidates include the endpoints. Now, this idea is called the Extreme Value Theorem, EVT for short, and we've been using Extreme Value Theorem for a long time. What it says officially is if f of x is continuous, so it has to be a connected graph. No jumps or holes or things like that. Otherwise, you can't apply this. It has to be on a closed interval, meaning you have to have endpoints. You have to have edges. Closed interval, okay? Like the window, like the picture that we were just talking about, right? That was a closed window. If those things are true, then f of x must have both an absolute max and min. So there's a guarantee you're going to get a max and min. And then it tells you that they're going to happen at a critical point on an endpoint. So it's a way of finding them, but it's also a guarantee. Now, just because you can't use EVT because it doesn't satisfy those preconditions doesn't mean the function doesn't have an absolute max or min. right? It's not guaranteed to anymore. Like if these things are true, you are getting a max min. If these things aren't true, then you can't use EVT, and you're not guaranteed to get max min. You might get a max and a min. You might just get a max. You might just get a min. You might get neither. So some issues. Continuous would be like if you had a vertical asymptote in the middle of where you're looking at, then that's not continuous, and you can't do EVT, right? Not continuous. Some kind of break in the graph. Right now, if it were connected, then we're all good, right? So that's one issue. And it depends on where you're looking at it. Like a graph might have issues, but if it doesn't have issues between your endpoints, then you're fine. Okay. It has to be on a closed interval. So if I just do a parabola and I don't put endpoints, well, this graph goes up forever and has no absolute max. It has an absolute min right here, but we don't get a max, and we can't test the endpoint, so we can't use the table. It just doesn't work, right? So a parabola itself doesn't have an absolute max. And you can't say it's infinity. It doesn't have an absolute max. But if we put a window around it, give it endpoints, it does. So here's the absolute min, right? But no absolute max. But as soon as we put a window on it, then our endpoints end up being the absolute maxes, right? And then we get an absolute max. So you gotta watch out. You can't use EVT all the time. So here's a couple examples. Okay, so let's see. Find the absolute max and min of this function. And so let's see. We need critical points and endpoints. The endpoints are given to us. The video is lagging. Oh well. And you want to make sure it actually meets the criteria. It has a closed interval, right? Is this a continuous function? It is a continuous function. It's a polynomial. All polynomials are continuous functions. Okay. And we need to find, so it is continuous. It's on a closed interval. You want to check these, right? It's got to be, yeah. Okay. So we got to find critical points. So we got to do f prime of x equals 6x squared plus 12x equals 0 undefined. We want to factor it. 6x plus 2 equals 0 undefined. So x equals 0 and x equals -2. These are our critical points. Now, they might end up being outside of our endpoints. Then we're not going to consider them. Now, we could, could we do a line check? Could we do first derivative test? Let me show you what happens if we do that. Sometimes you might be able to pull it off, but a lot of times you won't. And justifying it is a headache. So if we do this, just to show you, this is not what we're usually going to do. You could test like 1, and it would be positive, negative, positive. The graph goes up, the graph goes down, the graph goes up. We do have endpoints at -3 and +3, right? And we do have, so we have relative min and we have relative max, but is that the highest point? Well, this graph keeps going up over here, so it could be the edge. Can you tell just from this line check if this edge is going to be higher than that? You have no. Is this relative? This is relative min, absolute min. I don't know. Graph keeps going down over here, so this is not going to work. And even if it did in a special case, explaining it is horrible because you have to first justify relative maximum, and then you got to tell me why it's going to be an absolute maximum. So we're not going to do that. We're going to do the table, which is the way we've been doing it. So this is like those optimization problems, but way easier. You have to do all the geometry in the picture. You don't even have to figure out what the endpoints are. It's just given to you. So -3, -2, 0, 3. We're going to plug these in. So it's going to be 2 times -27 plus 6 times 9 plus 1, -54 plus 54 is 0 plus 1 is 1. 2 times negative 8 plus 6 times 4 plus 1. That's going to be 24 minus 16 is 8 plus 1 is 9. Plug 0 in. You get 1. We're going to plug 3 in. Positive 27. 6 times 9 plus 1. So it's going to be 54. Plus 54 is 108. Plus 1 is 109. So here's your max. And there's a tie for the min, which is okay. You only can have one max and one min. It might happen, the same value might happen in multiple places. So we're going to say the absolute maximum is 109 at x equals 3. The absolute minimum uses the same work. Don't need to do any extra work. It's the same exact work. Absolute minimum is 1 at x equals negative 3 and 0. Now, if we were to justify this, we'd say by extreme value theorem, checking endpoints and critical points. Just like we've been writing for a while. Right? So there you go. That's how you do it. Okay, here's a multiple choice one. The maximum value of this function on negative 2 to 1. So here's your endpoints. You have a closed interval, right? Closed interval. Gotta make sure you have that to use EVT. Is your function continuous? Yep, it's a cubic. So it's a nice smooth connected curve. So we got to find critical points. So we're going to take the derivative, right? We're going to factor it. Set it equal to 0 undefined, which you should show in your work. Don't just jump in to tell me what it is without showing me where it came from. So x minus 1, x minus 2. Label your work. X equals 1 and 2. Critical points. So we're going to do a table. It's the best way to do it. F of x, plugging back into the original equation. A lot of times I like to write it down. So we're doing negative 1, 1, and 2. So one of our endpoints and critical points are the same. Who cares? It's fine. If you get critical points that are outside the endpoints, don't even bother calculating. So this is going to be 2 times negative 1 minus 9 times positive 1 minus 12 minus 1. So this is going to be negative 11, negative 23, negative 24. Plug positive 1 in. And we get negative 7, 5, we get 4. Plug 2 in. So we get 16. 24 is 40. Minus 36 is 4. Minus 1 is 3. So here's the absolute min, right? Here's the absolute max. Same work. We want the max. So a bunch of you guys are gonna be like, "Oh, look, it's right here. It's 1." And oh man. Okay, did they say they wanted the x-coordinate of where there was a maximum value? No, they want the maximum value. That's the y value. Ooh, you got to be careful. Right? If we were to write this as an answer, we'd say the absolute maximum is 4 at x equals 1. Don't get tricked. The answer is E. Be careful. Make sure you sometimes ask you for the y value, sometimes ask you for the location. On free response, I always put both of them. It's safe. Multiple choice, you got to make sure you pick the right one. So today's assignment is partly out of the book and partly a worksheet with some free response problems to start trying. So try these out.